My topic is controversial, but true. So we're not diploid anymore, okay? And I'll explain why in the next few seconds. So what I'm going to walk you through here is a technological evolution over the last 50 years, but I'll do it fast. But it's really led to a diagnostic revolution in the last few years. So that is what a karyotype looked like around 1960. And what you can see is you can count from big to little, and that's about all you can do. So this methodology allows you to count extra or missing, but that's all, okay? And by the way, I just want to make sure everyone knows that the right count of human chromosomes is 1956, okay? That's the year we knew we had 46 chromosomes. It's not very long ago. Okay, so being able to count chromosomes allowed us to understand the cause of Down syndrome, which is, in most cases, a whole extra chromosome 21, and if sorry, Ronnie, go ahead. Down at the bottom there, you count from the longest is 1 and the shortest is 22, and down there there's 3 21s, okay? So, and you can count a missing or extra sex chromosome, or trisomy 13, or trisomy 18, but all you can do is count. Okay. Over the next 20 years, they were able to do something called a high-resolution karyotype, which now allows you to see light and dark bands. And there are wonderful human beings who have spent 20, 30 years of their life staring into a microscope and can actually see missing and extra pieces of light and dark bands. And I love them. I cannot do this, okay? But you can imagine that this is rather a subjective thing. A really, really good person does it really, really well, and a really lazy, fast person isn't. So this allows you to say some more things, and in fact we were able to recognize more syndromes. So I don't know if you can see on the top of that, that's chromosome 4. There's a little white area, a light band on the top that's missing on the other chromosome 4. That's a different condition called 4p- or Wolff-Hirschhorn syndrome. And kids have particular sort of characteristic facies and a lot of other problems. And we were able to recognize what that syndrome is based on this chromosomal abnormality. Okay, then along came a different methodology. You heard a little bit about it earlier today called FISH, which is fluorescence in situ hybridization. And when you do FISH, you actually label a piece of DNA with a fluorescent probe, and then you can hybridize it either to plain DNA or to a karyotype spread, which is what you have here. And you can barely see, you actually can't see this, but let me try to show you. There's a green band here, and a green dot here, and a green dot here. Those are the ends of chromosome 22, thank you. And then put it back on so people don't fall asleep because it's late. And then there is a red dot here, turn off for 1 second. And there's a red arrow here, but no red dot, okay? So it's a little confusing because it's a red arrow. But this person has 2 chromosome 22, and this one has this area, which is Q11, but this one doesn't. This chromosome is missing that band, okay? You can't see that. Even a really, really good person who spent 20 years looking under the microscope can't see that, okay? So this methodology allowed us to identify additional conditions. 22q11 deletion syndrome is a very interesting disorder, which I don't have time to tell you all about, but it has all kinds of different manifestations. You can have them all, or you can only have one part. And unfortunately, there's about a 25% risk of schizophrenia with this condition. So you can now pick up all kinds of conditions using FISH, but you're only going to find what you look for. So if you have a probe looking for an area, you will see whether it's there or not. But if you don't have a probe looking for an area, you won't know if it's there or not because it's not highlighted. Okay? So it's very useful if you have a question, but it doesn't let you look at everything. Okay. I just told you the limitations first. Now, the Human Genome Project showed us that the ends of chromosomes are particularly gene-rich. So people say, well, ends of chromosomes are gene-rich, let's look at the ends of chromosomes. So the next new methodology that came along was something called subtelomere FISH. So the telomere is the end of a chromosome, subtelomere just above the end, and they would have probes for each of the chromosomes. And that method allowed us to detect more problems. So we went up from about 1 to 3% of people coming in with either multiple congenital anomalies, so a newborn with all kinds of problems, or a person with developmental delay or mental retardation. You could, a karyotype, a regular chromosome test, the high-resolution kind, will pick up about 1 to 3%, the cause for 1 to 3% of those. This method doubled that. That's very nice. That's great, actually. We were very excited. But there's still a lot we're missing. Okay, and by the way, so that's what this shows you and it tells you how it does it. They did about 11,688 cases. Yield goes up about 2.5%, which is great. It's doubling, but it's still, you don't diagnose most things. The nice thing was it allowed you to identify new problems. So if you look at these kids' faces, and you don't have time to look at them at length, they all look a little unusual, but they don't look exactly the same. So a child with Down syndrome, no matter what ethnicity they come from, you know they have Down syndrome. It's a characteristic phase. With 1p36, they have dysmorphic features, but they're not identical. They have all kinds of other problems as well. And again, if a patient like this came into my clinic, I'm a geneticist, I see kids with problems, I know they have something and I'd want to do this test, but I wouldn't know, aha, it's this syndrome, because obviously everybody can see that. All right? Okay, so now a new thing came along. It's called a constitutional array. So a constitutional array combines the best of everything I just told you about. It looks at the ends of the chromosomes, and it looks for the known deletion or duplication phenotypes. So 22q11 deletion, you're missing a piece of 22q11. Williams syndrome is another one. There's a bunch of these. There were 40 of them in 2008. There were 100 of them in 2009, and we're up to almost 200 now. So this is a moving target. So every time you had to add more stuff onto the test, that would be really hard to do. It's probably useful and the subject of an ongoing large-scale clinical trial for pregnant people. Because when you do a test on a fetus, you want to know the meaning of what you see. Okay, it's a very different thing than if I see a child comes into clinic with me to see me, and has a problem. They clearly have a problem. It's very helpful if I can make a diagnosis, but the most important thing is to take care of that child and make sure that they get the services that they need. If you have a pregnancy, and you're going to decide to continue or terminate a pregnancy, you better know exactly what the information you're imparting means. It has to mean something to somebody. So this is going on right now. Okay. Oops, sorry. Let me go back one. Okay. So then a totally different method became available. Something called an array. Sometimes they're called oligoarrays. Sometimes they're called SNP arrays. Sometimes they're called chromosome microarrays. Sometimes they're called copy number variation arrays. You name it, they're basically the same thing. What you do is you take DNA from the person in question and a reference DNA sample, and often that reference DNA is actually pooled. It's from several people, same sex, okay? And you take them and put them together with a floor, and you do it in two directions, okay? And then you hybridize, and if it's the same, it's yellow. If it's too much, it's green, and if it's too little, it's red. And you get, the computer gives you a plot that looks like this. Now you're not looking under the microscope anymore. You're not looking at, a computer is doing this and giving, you're putting it on a slide, and then the computer reads the slide and gives you an output. So this is an example going across all the chromosomes that go from 1 to Y at the very end, and the line between the red and the green is normal, and this is a person with a normal result. There's some variation in there, but they're right in between those lines. This is a normal person. Okay, whatever that means. Okay, around the time people started doing this test, we discovered something we had absolutely no idea of. And it's actually quite embarrassing, but I'll tell you about it. And again, this is 2004. Okay, so it's like yesterday as far as I'm concerned. We found out that there was a lot of variability in copy number in normal people, okay? At a range between 1,000 base pairs and 1,000,000 base pairs, missing and extra pieces throughout the genome. Copy number variation is defined as blocks of DNA sequence that vary in the number of copies, so not more than one on each chromosome, and deletions or duplications are defined as more than 1,000 and generally less than 1,000,000 base pairs in length. And it turns out they're quite common. Now, before this paper in 2004, we knew that there was variation, usually clinically significant variation, so somebody has a problem if they have this problem, that was detectable by the karyotype stuff I showed you before. And we knew that you can sequence and find single nucleotide polymorphisms, change at one base pair, or small insertions and deletions of a few base pairs, or short tandem repeats. But nobody, and I mean nobody, thought about the fact that you'd have this kind of variation. Okay? How incredibly stupid not to have thought of that. We just didn't, we missed it. We didn't even have it on our radar. So why? Why are we so stupid? Well, David Valley calls this the Diploid Indoctrination. And the Diploid Indoctrination, and I've been practicing genetics for more than 20 years, and what I say to my patients is we all have 2 copies of every gene we have. One from our mother and one from our father, right? And Mendelian rules seem to apply in human beings, and so nobody even thought about this kind of variation.